Hello guys, today I am going to explain you how can we solve this problem Kth ancestor of a tree node. So basically this problem is from Leetcode's weekly challenge and it is tagged as a hard problem. The problem statement says that you are given a tree with n nodes numbered from 0 to n minus 1 in the form of a parent array where parent of I is the parent of node I. The root of the tree is given to be node 0 and we need to implement the function get kth ancestor, which has two parameters. One is the node number and the k, that means we need the kth ancestor that we need to find, and if there is no such ancestor we need to return -1. For example, for 1 there is no second ancestor. The kth ancestor of a tree node is the kth node in the path of the path from that node to the root. Alright, so for example, from 3 to 0, the first node, first ancestor is this one, second is 0 itself. So here, as you can see, the input are given such that first one will tell you the number of nodes, then this second is the parent array. Like for 0th node the parent is -1, for first and second the parent is 0, for 3 and 4 it is 1, and for 5 and 6 it is 2. And the queries are like, for the third node we need to find the first ancestor. So for third node first ancestor is 1, which is correct, and for fifth node the second ancestor seems to be 0, and yes it is. And for sixth node the third ancestor there is no third ancestor for any node in this tree, so it will be -1. Alright, so given that the k can be as big as 5 into 10 raised to the power 4, the number of nodes can also be that much only, and there can be at max these many queries. So now let's try to walk through few examples and see what's the best approach that we can follow. So let's take this example from the problem and let's try to understand what are the approach that we can take. So one most simple approach that one can follow is to do a DFS, and what you can do is basically simply call a DFS with the vertex that we have for now. Let's say for example we wanted to find some kth ancestor for this node. So what we could have done is we could have done basically a DFS starting from this node, and we'll keep a track of what's the current k that we have. So basically we can just simply have two things, DFS of v and k, and then here we can simply call our DFS recursively with the parent of v, or let me just remove this parent of v, and here we will decrease -1. That means we are going to check for one less level. So at any moment if k becomes 0, we would know that this is our node that we want, and otherwise if at any node if at any level this becomes the root node itself and this is not the kth node that we want, then we can simply return because there is no more node ahead, or we can just keep track because parent of root will be -1. So if at any moment if this v becomes -1, so we know that there is no more nodes left and this is impossible to get the kth node that we want. Alright, so for example if we wanted to find the first ancestor for 5, what we can do, we can just simply recursively call our function for parent of 5 with the k -1. That means parent of 5 is 2 and k -1 will be 0. So at this moment we see that k has become 0, so this will be our node. Alright, so for example if we wanted to get the second ancestor, so what we could have done is from here as well, now at this moment instead of this being 0, we would have k equals to 1 because 5 to 2 is the parent of 2 is the parent of 5, and here the k was 2 initially, and now k is decreased to be 1, and then from here again we will recursively call for the parent of 2. So parent of 2 is 0, and then we will decrease k by 1 again, so this also becomes 0, and as this becomes 0, we know that this is our node that we want. So 2 is our node, so what you can also understand is correct. So as you can see that this algorithm works very well. So what's the problem here with this algorithm is that this what we are doing is we are going traversing from one node to its parent node one by one, and this works very well when this tree is basically a balanced tree. Doesn't have to be a binary tree, it can be an array tree, but it has to be balanced one. So that why I'm saying it should be a balanced tree, because let's say if this is not balanced and this was a totally a skewed tree, so what we would be doing is for example, if this was the node, this was some 10 raised to the power fifth node in this tree, and we were to find its 10 to the power fifth ancestor as well, and in that case what we will always do is we will traverse from here to here, from here to here, from here to here, and then so on between all these nodes in between, and then we'll reach the root, and then there we'll find the correct ancestor. Similarly, yeah, we can just say any value which is bigger than 10 raised to the power 3 might give us time out here, because we are doing so many queries and all of them are taking these many operations to find the kth ancestor. So now you can sense what's the problem here. Why it works well here, because in this case the maximum amount of time that it will take is log of n, because the height will be basically log of n, where n is the number of node. So it was perfectly balanced, so it won't take more than this one. But here this can take around O of n. So to get the answer for q queries, we'll take O n q. However, here it would be log of n q. All right, so now you can understand what's the problem here, and now let's try to think how can we optimize this. But before talking about the optimized version, I want to also point out one key thing here, which is that the reason behind jumping one by one to its parent from every node is because we don't have any information for any node other than its parent node. So we only can jump from one node to its immediate parent, and then from there to its immediate parent again, because we don't know any other parent in already for this particular node. So anytime we are given this query to find some kth node from this particular node, we always would go from here to here, from here to here, and so on until we find the kth node. So one can argue that we can simply store all of its parents, like the first parent, the second parent, and the third parent and all. So storing means like pre-processing all these would also take a O of n square time, as well as it will take at max O of n square space. So this is not the most optimized approach. I mean, it's better to leave it like that instead of doing this and do all these O of n q operations. So yeah, now that I have also brought the most painful point, that because of this node not knowing its other node than its parent, immediate parent, so that's the reason we always do one by one jump. And so with that hint, we can realize that if there is a way for us to know some other kth ancestor for this node, not necessarily to be the kth ancestor that we want, but let's say some ith ancestor for this node, which can help us lead to the kth ancestor in quick time, that can help us in a very significant manner. So yeah, there is a very well known technique for this, and that is known as binary lifting. Now I'm going to explain you what binary lifting is and how it can help us solve this problem in very optimized way. So we saw that a normal DFS would not work in most of the cases, and storing all the parents for each node is also not going to work. So what binary lifting helps us do is, we can just by storing few parents of each node, we can find every kth parent for any node. So instead of each node storing all the parents, like all the ancestor of each node, like for example, instead of 5 storing its first parent or second and third and fourth, what we can do is we can store only few parents for each node. Like for 5 we can store 1 and then 3 and some. So with the help of this technique, we can easily find every for every node we can find if its kth ancestor within quick time. And so now we will try to see what all the parents that we should store for each node, so that we can get any kth parent quickly. So let's try to do this pre-processing, like to build a node parent table where we will try to store the parent, some parent of each node. So to build all these relations, we need to first understand what is initially given to us. Initially we are only given immediate parent for each node. Now let's utilize this information. Let me just first delete these two. So we know that immediate parent for each node is given to us, and let's utilize this information and try to see what are all the things that we should store to get any kth parent. So we know that for this, the immediate parent is this one. For 5 the immediate parent is 4, and for 5 the second parent is 3. So if we take a close look here, 3 is also the immediate parent for 4. That means for 5 the second parent is 3, which is equals to the first parent of 4. Alright, and 4 itself is a first parent, or the other way around, 4 itself is the first parent. Alright, so this gives us a hint that if we want to, let's say for example, similarly if you want to calculate the fourth parent for 5, we can simply go to the half of this. Like we can ask 3's second parent, and which is the second parent of 5 itself. So we can simply check whatever we want. Let's say we want some kth parent for each node, then what we can say is we will ask its k by 2th parent that give me his k by 2th parent. Alright, so basically k by 2 comma k by 2 will be our recurrence relation. Similarly, what happened here is we wanted to know second parent for 5. So what did we say? We said we will ask your first parent, that is the first 2 by 2 will be 1. So first parent of 5, that give me your first parent. Similarly, for once we are going to ask fourth parent for 5, we will ask third, who is the second parent of 5, that to give back this second parent for 3. So to generalize this, what we can say is we are given with some k parent, and we are kth parent of each node, and we are trying to store 2 into kth parent for from this given information. So now initially we were given the first parent, then we will be able to find the second parent for each node. Then using this second parent we can find the fourth parent for each node, and so on, 8 and 16. So this is what we are going to store. For each node we are going to store its 2 raised to the power ith node, ith parent, where I would be ranging from 0 to log of n. And as you can see that to generate 2 to the power ith parent, we are using the previous information that is given to us. So we can do this pre-processing using dynamic programming, and overall complexity of storing these parents would be n log n, where n is the number of nodes and n log n will also be the space complexity for storing all these parents for each node. Alright, so now let me just quickly show you before going ahead that how can we do this, or how can we store this by doing the pre-processing. So this is where I am doing this pre-processing. I have created a dp table where dp of I comma j explains you the 2 raised to the power jth parent of I, node I, and the max will be n log n. So this is where I'm storing log n base 2, and initially all of them should be -1. I initialize dp table with -1, and then what I'm doing is in the pre-processing, so basically the first parent, the first immediate parent, that means 2 raised to power 0 should be v2u, because we are given here the parent vector. So for each node I, the parent of this node is parent of I, so u is the parent and I is the, yeah, v is the node that we want to generate the parents for. So if we take a look here, this is what our base would look like. We are given that for v, the immediate parent, that is 2 raised to power 0th parent, that is first parent is u. So this is what I have assigned. dv of 0 would be this. Keep in mind that this is not 0th parent, this is 2 raised to power 0th parent. And similarly, when we are trying to build v's 2 raised to power ith parent, it will be from its 2 raised to power I minus 1th parent. Basically what I was showing here is when we are trying to build this the parent for this fourth parent for 5, what we said is we will find 4 by 2th parent. So basically if we are going to build 2 raised to power ith parent, then we would need 2 raised to power I divided by 2th parent, which will be 2 raised to power I minus 1, and hence that's why I have written here 2 I minus 1, because this is telling us 2 raised to power I minus 1, and this is the parent itself. So basically for this case, if you remember, from 5 to 1 we wanted to know the parent, which is the second parent of 5. So this is the parent also, and from this parent also we want is this 2 raised to power I minus 1th parent of this node. So that's what I've done here. So basically from dp of to generate 2 raised to power ith parent for v node, we need to have its 2 raised to power I minus 1th parent, and then from there we will need 2 raised to power I minus 1th parent for this node. And at any moment if we see that the parent is -1, then we will stop our this process of building the dp table, because we cannot have any more node ahead of the root node. So now let's try to see how can we find any kth number, because here as you can see, every time we are only storing a node which is only storing the parent which is in form of 2 raised to power some value. And what if the k itself is not some value which is directly in form of 2 raised to power some value? So for example, if k is 13 or k is 5 or k is 3, what can happen there? So let me just explain those things. Alright, so now let me explain you how can we find the kth node. So now that we have stored every 2 raised to power ith parent for each node, if the given k is in form of 2 raised to power some I, then we can directly fetch it from our dp table that we store while doing the pre-processing. But what if k is not in form of 2 raised to power I? Let's say for example k is equals to 7. So what we can do is we can write 7 in form of some 2 raised to the power I values, which will be 2 raised to the power 2 plus 2 raised to the power 1 plus 2 raised to the power 0. So if you check its binary representation, it is 1 1 and 1. So this can also be written as this in this form. So here what it's shows us that what we can do is we can try to make a jump from this node in one of these forms, like in one of these steps, like in any order. We can pick these ones in any order, like these we can treat as number of steps that we are going to make jump. So for example, what we could do is to reach to 7 from here to here, what we could do is we could simply first make 4 jumps. So we can just go to the fourth parent of this node, and then from there we can take any, let's say we can choose the 0th one. So we can maybe 2 to the power 0 means we can go to the first parent, that is 1, and then from here 2 to the power 1 means the second parent from here. So this will lead us to this path. And if we choose the other way around, like from 2 to the power 0 first, then the first parent is here, then from there if we want to go to the second parent from here, so this is what, and then from here we want to go to the fourth parent from here. So this way also we can reach. You can also try from 2 to the power 1 first, so we can directly jump from here to the second parent, and then from here to we can check for the fourth parent, which will be this one, and then from there we can reach out to this one. So as you can see, the order here doesn't matter. Whichever we want, we can pick that one first. The only thing is that we just want to check whichever bit is set in its binary representation, and then only we will make a jump to that particular 2 raised to power that particular bit. So let me explain you pretty quickly through the code now, because I think it can better be understood through the code. So what I'm doing is, for a given node we want to find the kth parent. So what are we going to start? We are going to check is from 0 till whatever the maximum size that we can traverse till, which will be log of n, the number of nodes in the tree. And then what I'm checking, so here this part checks whether this ith bit is set in this k or not. That means in the binary representation of k, for example in our case when we took 7, all of these bits are set. So here we will traverse from 0, 0, 1 and 2. So it will in our case it was all 1. So we only need to make jumps where this particular bit is set to be 1, and then once we see that this bit is set to be 1, then what we can do is we can just change our node to the parent node. So from here we saw that if this node was this bit was set, then what we did is we made a jump of 2 raised to power I, and then the new node is this particular node, this, and that's what I'm doing here. So the new node will become the parent of this particular node with 2 raised to power ith parent. The 2 raised to power ith parent of the current node. And then if at any moment if I have reached the -1, that means there is no more node left, and that means this current node was the root node. So at that means that we don't have the kth ancestor. So for example in this case, if we want to find from here, let's say if we want to find fifth parent or more than second parent, then there is no such value, so we need to just return -1 from there. Otherwise in the end, whatever will be the value stored in node will be the parent node, that the kth parent or the kth ancestor node. So yeah, I think that's it. I was able to explain you guys in simple terms, or if there is anything that you think is not very clear, or if there is anything that you want me to revisit, please let me know that in the comment section. I would be happy to help. And yeah, thanks for watching this video guys.